Welcome. In this video, we're going to take a look at a concept known as the cross product. And the cross product between two vectors, which is denoted by v cross w. So we'll often say v cross w. This looks like v times w, but that multiplication sign actually denotes a cross product. So when you're working with vectors and you see this, it's not a dot product, it's a cross product. And the cross product is a vector. So unlike a dot product that is a scalar, a cross product is a vector that is perpendicular to both v and w. So in this picture here, we have two vectors. We have v and w, and there exists some angle between them called theta. And then this vector here that is denoted v cross w is in fact perpendicular to both v and w. So perpendicular there and perpendicular here as well. And the question is, how do we find such a vector? And there are many applications where we would want to do this. So v and w could represent two vectors along some sort of walkway, some sort of inclined walkway. And we want to be able to find a vector that is perpendicular to it, which could represent something that we're going to pin to the ground or other possible applications. We could pick any two vectors that lie along the walkway. So v and w are not unique vectors because if we remember, this is a whole surface of vectors. And so we could possibly pick anything that is inside of this plane. So that's an important thing to note, that to find a vector that is perpendicular to a plane, we only need to find two vectors. So how do we find this? Well, first of all, we have to revisit some of the properties that we know about perpendicularity of vectors. So let's denote v to have components v1, v2, v3. W will have components w1, w2, w3. And to keep things simple in terms of notation, v cross w is a perpendicular vector. So for the moment, let's denote that by the vector n, like the normal vector. And it has three components that we don't yet know. Let's denote those x, y, and z. So we form two equations, and often solving for something involves forming some equations and then solving that system. So if we look at the dot product between this cross product vector n and one of the original vectors v, well, since n is perpendicular to v, that is because n is perpendicular to both v and w, these dot products should equal 0. And if we put it in terms of the components, n is the vector that consists of components x, y, and z, and we're going to dot that with the vector that contains components v1, v2, and v3. When we multiply these together, we get x v1 or v1x plus v2 y plus v3z, and that has to equal 0. So there is our first equation in the system. So we need to satisfy this. X, y, and z should be chosen so that this dot product works out to be 0. Now that's not enough. We also need to make sure that it's perpendicular to w as well, and it's the same vector consisting of components x, y, and z. And when we dot that with w1, w2, and w3, we should again get a 0 dot product. So here we get w1x plus w1y, w2y, excuse me, plus w3z, and that dot product has to equal 0 as well. So now we have a system of two equations that when we solve this system for x, y, and z, we should be able to get a vector that's perpendicular to both. Now we're not going to go ahead and solve this here, but we can show that this system of two equations containing three variables can be shown to have the following solution. So the components of n, for visual reference, that is again this vector here. We're going to refer to that as n. And that vector right there is going to have, okay, that's the cross product between v and w. It has these three unknown components. Those three components will look like this. So the components of the v vector, v2, multiplied by w3 of the w vector minus w2 multiplied by v3 of the v vector. That's going to produce our x component of this normal vector. The y component will be formed in this way. That's the negative of this entire quantity. So whatever we get there, we're going to flip the sign. And then the z component is going to be v1 w2 minus w1 v2. To better believe that this is the result, we just need to verify that this claim, that we claim that this vector is perpendicular to both v and w. So if we find the dot product, we should get 0 when we multiply this out. So in the top, when we conduct the dot product, it's going to be v1 multiplied by this entire quantity here, so that'll get distributed in, and we'll have v1, v2, w3, and then minus v1, w2, v3, minus v1, and I'll just list the v's first, v1, v3, w2. And oh, this is going to be a dot product, so this is just going to be a single number that we get. And now we're going to add to that the dot product between these two components here in the middle. And so here we'll have v2 times v1 w3, the negative of that. So that will be negative v1 v2 w3. And then v2 will distribute into the negative, which will be actually a positive, w1 v3. So that will give us v2 v3 w1, v2 v3 w1, and then we're going to add to that one more component, which will be the product between v3 and the bottom component here. So multiplying v3 into this first term will be v1 v3 w2, and minus v3 times this term, which will be v2 v3 w1. And now we just have to check, is this going to be equal to 0? So hopefully things will cancel out here. So I have a positive v1 v2 w3 here. Then I'm going to have a, right here, negative v1 v2 w3. So those will cancel out. Here I have a negative v1 v3 w2. Here I have a positive v1 v3 w2. And then lastly, I see that v2 v3 w1 and negative v2 v3 w1 will cancel out, and that will produce 0. So that checks out. So far, so good. So far, our formula is correct. Let's verify it here. So again, we'll conduct the dot product. So here we'll have w1 multiplying this term, v2 w1 w3. So v2 w1 w3. And then we'll have w1 times this term, which will be v3 minus v3 w1 w2, just keeping them in order so they're easy to see as they cancel out. And then w2 will multiply the negative of v1 w3, which will be v1, or negative v1 w2 w3. The second component will be w2 times negative the positive of w1 v3, so that'll be v3 w1 w2. And finally, the third term will be w3 times this, which will produce v1 w2 w3 minus v2 w1 w3. And once again, all we need to do is just verify that each term has a cancellation component. So there I have a v2 w1 w3, and down here I have a negative v2 w1 w3. Here I have a negative v3 w1 w2. Here I have a positive v3 w1 w2. And then lastly, we should see that these two cancel each other out. Therefore, our dot product is 0. So perfect. So we now know that this formula for the cross product is the correct formula for, once again, finding a vector that is perpendicular to two given vectors. Now this is a difficult formula to remember. There is an easier way to remember this, and it is almost intuitive. So let's go ahead and take a look at a quick way to calculate this. So we can use what's called a matrix. And in the matrix, what we're going to list across the top row is our vectors I, j, and k. And if we remember, I is simply the vector 1, 0, 0. J is the vector 0, 1, 0. And k is the vector 0, 0, 1. So I, j, and k really just stand for the x, the y, and the z components. And then in the the second row, we have the components of the first vector listed. So second row has to contain the first vector in that cross product. The third row will contain the components of that second vector. And these brackets around this denote what's called the determinant of a matrix, and we'll describe that in just a moment in terms of how to do it. So this can easily be found by following the principles. If we want to know the I component, if what we do is we cross out the column in which I is in, and we cross out the row in which I is in, then the remaining little submatrix that we have left, this is 4 components, if we calculate V2 times W3 along the diagonal from top left to bottom right, that will give us the first term in the I component, and then subtract away the product between the bottom left and the top right diagonal, W2 V3, then we get the I component. To get the J component, it's going to be the negative of what we would get in the same fashion by taking the column in which J is, crossing that out, the row in which J is, crossing that out, and then the 4 components that we have here are V1, V3, W1, and W3. And if once again we look at the diagonal from top left to bottom right, V1 times W3, and then subtract away the diagonal product from bottom left to top right, W1, V3, subtract that away and take the negative of it, that gives us the J component. So this is a key here to remember if you are using this formula, to remember that the J component gets negated. So it's the same principle as the I component, but it's the negative of it. For K, we're back to a positive coefficient, and as you probably guessed, we take the column in which K is, cross that out, the row in which K is, cross that out, the 4 values that we have left, top left times bottom right, gives me V1, W2, subtract away the product between the diagonal, the bottom left times the top right, W1, V2, and that gives me my K component. So it's a real simple way to calculate this without having to remember all the individual products. So let's take a look at an example. Here we have V is 1, 0, 1, W is 1, negative 1, 2. We want to find the cross product between them. So what we're looking for is the vector that is perpendicular to both of these. And then we're going to prove that, in fact, this vector is perpendicular. So to create this, we're going to set up that determinant matrix and find the I, the J, and the K components. So V cross W, the first row is going to consist of I, J, K, and second row is going to consist of the components of the first vector listed, 1, 0, 1. W is 1, negative 1, 2. So to find its components of V cross W, we now need to build this vector by finding its 3 components. And we can list it in vector form, or we can list it in I, J, K form. And we'll do it both ways to show that they're identical. So the first piece of the process is to cross out the row in which I is in and the column in which I is in. And so that's the first column, that's the first row. And to get the I component, I just need to compute what we call the determinant of this little submatrix. So for the I component, now I'm not saying this is equal to I, I'm just saying this is the I component. It's going to be 0 times 2 minus negative 1 times 1. So that comes out to positive 1. And so that means our I component is 1. To get our j component, we're going to do a similar process. We'll take away our crossed out I column, and now we'll go ahead and cross out our j column. So there's our j column, there's our j row. The resulting values will be 1 times 2 minus 1 times 1, and it's going to be the negative of that. So 1 times 2 minus 1 times 1. That's going to give me 1 in the parentheses minus 1 after I take the negation of that. And so now I know that my j component is negative 1. So I could also write minus 1j. Now it's not the case that the j component will always be negative. We're just taking the negative of whatever value is in that parentheses. So go ahead and now focus on our k column. And to get that, we'll go ahead and cross out the k column, cross out the k row, and find the determinant of this resulting 2 by 2. So we'll have, for the k component, we'll have 1 times negative 1 plus 1 times 0, which comes out to negative 1. So my k component is negative 1, and here are the two forms in which I can proudly state that I found the cross product. So we're claiming that this vector n, that this is perpendicular to both 1, 0, 1, and 1, negative 1, 2. We'll go ahead and take a look at a graph of this in just a moment, but let's just go ahead and check our work. So to verify, let's compute the dot product between n and v. And so that's going to be 1, negative 1 times v, which is 1, 0, 1. We can see we get a positive 1, 0, negative 1. So that will be 0, and that's a good sign. And now we'll do the same thing to check our work for n dot w. 1, negative 1, dotted with 1, negative 1, and 2. And so here we'll have a positive 1. Here we'll have another positive 1, so that's 2. And then add that to negative 2, we'll in fact get 0. So this is just a numerical verification that our particular example worked out, that we didn't make any mistakes. We've already proven that the formula works. Now we can actually visualize this. Here's a little applet where you can type in two vectors. It'll output the cross product between them. And so we see here that in our visual, there's the vector. There are our two vectors. So one of these is going to be 1, 0, 1. That's going to be this one here. 1, 0, 1 is 1 unit this way, 0 units to the right or left, 1 unit up. And then this vector here is the vector 1, negative 1, 2. And so this plane is actually the plane that these two vectors form. These two vectors lie along this plane, and we can see that that cross product is shown here. That's the vector 1, negative 1, negative 1. So you can see 1 this way, negative 1 unit this way, and 1 unit down will take us to the tip of that vector. You can see there that GeoGebra, in fact, indicates there's a 90-degree angle between them. Now, what would happen if we reversed the order in which we listed those two vectors? So in our matrix, if we still listed I, J, and K, but instead we wanted to find the cross product between W and V. So if we did W cross V, that would indicate that we need to put the W vector, its components, in the second row, which is 1, negative 1, 2. And down the bottom, we'd list the V vector, which is 1, 0, 1. And to find this result, so we would once again, let's try to do this visually. We'll cross out the I column and the I row. So negative 1 times 1 plus 0 times 2 is negative 1. It'll be negative 1i. And then we're going to do minus whatever value we get by crossing out the j column and the j row. So 1 times 1 minus 1 times 2 is negative 1. So that's going to be minus a negative 1, j, plus something k. Okay, so cross out the k column, the k row. 1 times 0 is 0. Minus 1 times negative 1 is positive 1. So we'll get plus 1k, which is the same thing as listing this out as negative 1, 1, 1. So you notice that that vector right there is very, very similar to the vector that we obtained up here. Here we obtained 1, negative 1, negative 1. That's the vector that points perpendicular out in this direction. negative 1, 1, 1 is just a scalar multiple of our 1, negative 1, negative 1 vector. So if we look at the relationship between v cross w and w cross v, we see that negative 1, 1, 1 is really just negative 1 times the v cross w vector. So they're just negatives of one another, and this is w cross v. So what's the relationship between them? Well, they're equal but opposite signed. So if I put a negative 1 here, that will work, or I can just say it's the negative of w cross v. So it's going to be the same vector, but it's going to point in the opposite direction, and it's still going to form a perpendicularity to that plane that those two vectors are on. So that indicates that cross products are going to have some properties. And here are the three most valuable ones. W cross V is related to V cross W by being negatives of one another. So these are just opposite signs. Also, sometimes you want to scale a vector before you take a cross product. The second property just says that it really doesn't matter where you put that scalar. So you could find the cross product between v and w first, and then scale the whole result by that constant. Or you can scale v by the constant, and then find the cross product between that result and w. Or you could scale the w vector by that constant, and then take the cross product between v and that resulting vector. And then this is kind of more of a distributive property. And these may seem obvious, but when you're working with vectors, you can't assume that all of the same properties hold. So you may say to yourself, well, this is duh, I can see that this would be true. But remember that this is a distributive property for vectors. So when you establish a new distributive property for a new type of system, you still have to verify that it works. So this just says that if I want to find the cross product between u and the sum of two vectors, I can add those two vectors first, and then find the cross product between u and that result. Or I could sort of distribute u to both of those vectors, and notice that whatever vector is out in front is going to distribute to be in the front of the vector that it's distributing toward. So u cross v and v cross u are not going to produce the same result. If you switch the order, you'll get the negative value. So it's important that whatever vector is distributing in, that it stays on the left. So this equality indicates that we could do u cross v, then u cross w, and then finally add those results. And we get the same answer as if we added the two vectors v and w first, and then took the cross product between u and that result. Now it turns out that the cross product actually has some significance when it comes to the magnitude of v cross w. We'll make this claim and we'll provide some intuition here. The magnitude of the cross product is geometrically significant. In fact, the magnitude of the cross product gives us the area of the parallelogram formed by v and w. That seems like kind of a weird thing to do. This property, that it's the area, that the magnitude of the cross product gives us the area of the parallelogram formed by v and w, is really just a result of the mathematics that takes place. So when we set up the system of equations to find the components of this cross product, we actually unintentionally also happen to find a vector that's perpendicular to both, but also has the property that its magnitude is the area of the underlying parallelogram. So to indicate this, here I have two vectors, 1, 0, 0 is v, and w is 0, 2, 0. So the z-axis is sort of coming out right here, but we're ignoring the z-axis because both of these lie on the xy plane. So we're kind of looking down at these two vectors, and the parallelogram that they form, we should also point out that these happen to be perpendicular to one another because they point along the axes. So if we completed this parallelogram, basically by taking this vector and putting it on the tip of the v vector, and then we also took the v vector, the w vector, and moved it parallel to its original component, then we get this completed picture. We can see that this is just a rectangle, And that rectangle will have an area. So this is a perfect 90-degree angle here. So this is a perfect rectangle. And we see that this side is of length 2. And we see that this side is of length 1. So if we found their area, the area of this rectangle is 2 times 1, which is 2. At the same time, and we didn't calculate this cross product, but this is the cross product. If you dot it with V and you dot it with W, you can see you get a 0 dot product, indicating that this is in fact perpendicular to both. If you find the magnitude of 0, 0, 2 vector, then you get the square root of 0 squared plus 0 squared plus 2 squared, which comes out to 2. And we see that this vector, or this value and this value are the same. So the magnitude of the vector that's perpendicular to both these guys, its magnitude is equal to the area contained herein. That's kind of an interesting feature and pretty cool, really. But of course, that angle doesn't have to be 90. That was just the simple example to be able to demonstrate. What if we had the vectors 1, 0, 0 and 4, 3, 0? So we kind of took this vector here and we slanted it this way, came up with the vector 4, 3, 0. So our parallelogram would be basically taking the two sides and like so, and make it a little bit longer here. There we go. And now we can also take a vector from here to the tip of our other vector that we just drew. And now we have a parallelogram. So parallelogram means that these two sides are parallel. This side and this side are parallel. And so now this angle here is just some angle theta. So to find the area of this parallelogram, first of all, we should note that the area of a parallelogram is the same as that for a rectangle. It's base times height. We've got to be careful because although the base is the length of this vector here, which is 1, that length right there is 1, because it's the vector 1, 0, 0, we really need to be able to think about the length of not this vector, but the height of the corresponding parallelogram. So this is going to be the height right here. So to multiply base times height, we see that the base is 1, and that is simply the magnitude of our v vector. So 1 is the magnitude of v. And so we want to know what's the magnitude of, we're going to need to know the magnitude of this vector as well in order to be able to get that height. So to make this more general, we could say that the area is equal to the base, which is the magnitude of our vector v, multiplied by the height. Now the height is a little trickier to find, but not impossible. We just need to use a little bit of trigonometry here and take advantage of the geometry. So if that's theta, then this angle here is also theta. And if that's the case, then we could say that and this vector here is the same as the 4, 3, 0 vector here. So this blue side has a length of magnitude of w. So to get a relationship involving height, perhaps theta, and the magnitude of w, I could say that the sine of theta is equal to the height divided by the magnitude of w. Now I want to solve for height, so I can multiply both sides by the magnitude of w, and I get the magnitude of w times sine theta equals height. So to find the area, I need to multiply the base, which is the magnitude of v, times the height, which is w, magnitude of w, times sine of theta. So we just established a general formula to find the area of that parallelogram. So to actually find the area of that parallelogram, that's going to be this region here. To find the area of that, we have to actually calculate what the magnitude of v is. So the magnitude of v, we've already listed as being 1, which would just be the square root of the sum of the squared components. The magnitude of w, calculated in the normal way, would be the square root of 4 squared plus 3 squared plus 0 squared. So that's going to give me 16 plus 9 is 25. The square root of 25 is 5. And to calculate theta, the angle between the two angles, the angle between the two vectors, we know that we can use the law of cosines to do that. And from our derivation, we know that theta is going to equal the arc cosine of v dot w divided by the product of their magnitudes. And so the dot product between v and w, which are our vectors 1, 0, 0, and 4, 3, 0, the dot product is going to be 1 times 4 plus 0 plus 0, which will just be 4. So that's going to equal the arc cosine of 4 divided by the magnitude of v times the magnitude of w. We already have those. That's 1 times 5. And so that's going to be the arc cosine of 4/5, which equals about 36.87 degrees. Now to find the area, that's going to mean I have to now plug those things back into this formula. I have to take the magnitude of v, which is 1, times the magnitude of w, which is 5, times the sine of 36.87 degrees, and that comes out to approximately 3 square units. Now, we're claiming that that's equal to the magnitude of the cross product. So the cross product is v cross w, which was given to us in this problem. V cross w is going to be the vector 0, 0, 2, or that is 0, 0, 3. So the magnitude of the 0, 0, 3 vector, you can maybe see this already, but the magnitude of that is going to be the sum of the components squared and the square root of that, which is going to come out to be 3. So the fact that this magnitude of the cross product matches the area of the parallelogram, again, justifies that the magnitude of the cross product is the area of the underlying parallelogram formed by any two vectors. So that's a neat little property. Now we can also use the cross product in more creative ways. For instance, we wanted to find the equation of a plane given 3 points. And that's not always super easy to do. The only time we can really do that based on current methods is if the 3 ordered triples have one of the inputs held constant. So for these 3 ordered triples, it's not too tricky to find the equation of the plane, which we recall is of the form z equals mx plus ny plus some sort of z-intercept. To figure out the slope in the x direction, we just have to look at a situation where only the x value increases, but the y value does not. So we see from here to here, between these 2 ordered pairs, the only difference is that, the first and the third values is that the only thing that's changed is the x component has gone from 0 to 1. The y component is 0 in both triples, and so therefore we could say that the observed change of 2 units in z, so 10 to 12 is a 2-unit increase when we increase x by 1. So that means the slope in the x direction is 2. And then to find n, we just need to find 2 ordered triples where the y value changes, but the x value is held constant. And so we can see that from here to here, from this ordered pair to this ordered triple to this ordered triple, the only thing that changes is x is held constant, and the value of y changes from 0 to 1. And the corresponding change in z is from 10 to 14 per a 1-unit increase in y, so this will give me a slope of 4. And the first order triple already tells me what the z-intercept is. When I plug in 0 for x and 0 for y, I should get c equals 10. So that's possible to do without any fancy formulas. But consider these 3 order triples, negative 1, 3, 0, 3, 2, 4, and 1, negative 1, 5. We see that there's nothing from every ordered pair to every other ordered pair. There is a change in both the x and the y components. So we cannot utilize this process. So what do? Well, we know how to find a vector that is perpendicular to the plane formed by these 3 points. And then we can use the fact that a normal vector and one point on the plane can form the dot product equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught. We took advantage of the dot product to say, hey, if you have one known point on a plane and some arbitrary point on the plane, and a vector that is perpendicular to that plane that consists of the normal vector n equals abc, then we can compute this vector here. Given 2 points, the displacement vector is simply the difference between the x. So for this ordered pair, the x value is just generically x. For this ordered triple, it's x naught. And do the displacement for the y's and do the displacement for the z's. So since this vector is in the plane, which is perpendicular to this normal vector, the dot product between n and this vector is going to equal 0, giving us this formula here. So if we just have these 3 ordered triples to find the equation of the plane that passes through these 3 points, let's first find a vector that is perpendicular to 2 vectors formed by these 3 points. So how do we find 2 vectors? To find 2 vectors, if I have 3 points, and I'll just pretend that these are A, B, and C, rotated properly to make it look like we're looking down on them, then I have a few different options. I can form a vector from A to C, or I can form a vector from C to A. I can form a vector from A to B, or from B to A, or from C to B, or B to C. It really does not matter. The key here, though, is that these 3 points are all coplanar, meaning they all lie along the same plane. So imagine that this is our plane. Those 3 points are on that plane. And if I could find 2 vectors inside of that plane, then I can certainly find a vector that is perpendicular. So let's form one from A to C. To get a vector from point A to point C, I have to take the displacement. So from A to C, our x component goes from -1 to +1. That's an increase of 2 units. So in other words, we'll do point C minus point A. And that's going to give us 1 minus -1 is 2. -1 minus 3 is -4. 5 minus 0 is 5. So there I have a vector from C to A. And maybe I shouldn't call that C minus A. Maybe I'll just call that CA, vector CA. Vector AC. It's a vector from A to C. And now I can also form another vector, and I'm just going to choose from A to B. So from A to B, there's my vector, and that's going to be the difference between the values in point B and point A. So 3 minus -1 is 4. 2 minus 3 is -1. 4 minus 0 is 4. So now I have my 2 vectors, and now I just need to find the cross product between these two. That doesn't really matter whether I do AC cross AB or AB cross AC. We just need any vector that is perpendicular to both of these vectors. So let's just go ahead and say AC crossed with AB. So without running through the computations of this, the vector that we get is going to be listed. So if we had computed that cross product, we get -11, 12, and 14. So what we've just found is a vector that is perpendicular to both of these vectors. I'm going to draw that on here just to put this picture together. So here we have our vector, and we'll just kind of draw it like this. And we'll say that that vector is perpendicular to both AB, and it's also perpendicular to AC. Now, because we have one point that is on that plane, we could pick any of these points really, but let's focus on point A, which is the point -1, 3, 0. And then our normal vector, our n vector, is now -11, 12, and 14. So because we have one point in a plane and we have a vector that is normal to it, we can now utilize this dot product approach to finding the equation of that plane. So let's go ahead and do that. So what we'll do is we'll take a, which is negative 11, times x minus x naught. So that's going to be x minus negative 1, plus 12, it's our b, times y minus y naught, which is y minus 12, y minus 3, plus the c component, which is 14 times z minus 0. And we know that that dot product equals 0, since this vector is perpendicular to the plane. So now we have our formula, negative 11 times x plus 1, plus 12 times y minus 3, plus 14 times z equals 0. And if we wanted to, we could solve for z and get the equation of that plane. So that's one way we can utilize the cross product and the dot product to simultaneously allow us to then find the plane, equation of the plane that goes through 3 points that may not be spaced the way we want them to be. Now, would it also work for the points that are spaced like this, as in this example? Absolutely. We should get exactly z equals 2x plus 4y plus 10 if we were to use this approach we've taken here. But this approach works best whenever those points are not conducive to the types of behaviors we want. Another neat little application of working with cross products is, suppose we have 2 planes, and here we have, in particular, z equals 0, which, z equals 1 and x equals 0. So this plane here is x equals 0. This plane down here is z equals 1. So z equals 1 is just a horizontal plane that rests 1 unit above the xy plane, and x equals 0 is a vertical plane that runs entirely across the y-axis at x equals 0. And one of the things we may want to do is to find the line of intersection, or to think about the line of intersection between those 2 planes, which is right there. And that line of intersection contains infinitely many vectors. And maybe we want to find a vector that lies along that line right there. So how do we go about doing it? Well, one observation we can make is that if we start off by finding vectors that are perpendicular to our planes. So let's just say here we have a point that's on this plane, and that vector is going to point perpendicularly to that plane. So imagine that this angle right here is a right angle. And simultaneously, if we find a vector that is perpendicular to z equals 1, it's going to point straight up, and that's going to be a 90-degree angle right there. Then those 2 perpendicular vectors, if we think about this, form a plane themselves. And if to those 2 vectors, so let me complete this picture like so. If we take that plane then and find a vector that is perpendicular to it, guess where it's going to point? Well, it's going to point parallel to the line of intersection between those 2 planes. So can I think of a vector that is perpendicular to the plane x equals 0? Well, one such vector just has to point in the x direction, and one such vector would be the vector 1, 0, 0. That would point directly away, in the positive direction. So let's actually use negative 1, 0, 0, since these are increasingly more and more negative x values. And then this vector here is just perpendicular to the xy plane. So anything where the z component is non-zero will work, and where the x and y components are both 0. So that's going to be for this vector here. And now we need to find a vector that's perpendicular to both of these vectors, and we know how to do that. We can do that by finding the cross product. So if we find the cross product between 0, 0, 1 crossed with the vector negative 1, 0, 0, that should be parallel to the line of intersection between those 2 planes. By computing this cross product, we would get the vector 0, 1, 0. And 0, 1, 0, if we think about where that points directly in only the y direction. Points this way. 0, 1, 0, it points out along, and we can clearly see that that's parallel to that line of intersection. So the strategy is to find vectors perpendicular to our planes. So step one. Step two is then to find the cross product between those two vectors. Here we were able to do that intuitively because we could already figure out what vectors are perpendicular to the two planes that we're dealing with without having to do any real heavy mathematics, and then compute the cross product between those two. So step one involves finding these two guys, and then step two involves finding the cross product between them. Now, given the equation of two planes, this is actually a lot easier than it sounds. To find a vector that's perpendicular to that plane, all we need to do is think about this equation, 2x minus 3y plus 5z equals 2. If I move that 2 over, and let me just bundle it with the x, doesn't really matter which one it bundles with, but I can factor out a 2 more easily from that term, I get this is equal to 0. Now, this is really 2 times x minus 1 minus 3 times y minus 0, or plus 0 if you wish, plus 5 times z plus 0 equals 0. And this point 1, 0, 0 is going to be a point that's on that plane. And the vector 2, negative 3, 5 is going to be a vector that's perpendicular to that plane. So we're basically using the dot product between a vector on the plane and a vector perpendicular to the plane. So its normal vector would be the vector 2, negative 3, 5. So that would be normal to plane. And you see that that's really just a matter of picking the three coefficients from x, y, and z, respectively, to form that perpendicular vector. So if you're given the equation of a plane, it's pretty straightforward to grab that normal vector. Again, 4x plus y minus 3z equals 7. I don't really need to rearrange things because I'm going to factor a 4 here, a 1 here, and a negative 3 here. So the vector 4, positive 1, and negative 3 is, again, normal to that plane. And now the last task is just to find the cross product between these two. So, and again, it doesn't matter what order, whether that vector points, in this case, here's my line of intersection. We don't really care whether that vector points this way or whether it points this way. We just want a vector that is on that line of intersection. So let's just do 2, negative 3, 5, crossed with 4, 1, negative 3. And we get the vector 4, 26, 14. So we can say that the vector 4, 26, 14 is parallel to the line of intersection between the two planes given. And we now know how to work with perpendicularity. We can extend that to working with parallel vectors. And there are many cool ways in which we can use cross products to help us strategically find other things. But these were just a couple of examples where we could really get quite creative and answer some pretty difficult mathematical questions.